c'est de temps en temps, c'est borné avec le petit attentif, plus grand que ça. Mais donc l'invite est vraiment grand.
Tu peux faire des petits morceaux sympas.
Faire une grosse orbite. De toute façon, si vous avez des petits, là, c'est pas très grand.
Non, non, mais...
Oui. On genre ça plutôt bon pour les arabes. Ils sont pas dans la même orbite alors.
Non, à chaque fois je prends...
Ah, il en est de plus en plus grand.
Bon, jag fan vet inga också. Okej.
Vad som vill ni?
Jag får inte riktigt
Je pense que les réflexions pour déplacer le petit sur une chose de branche.
Yes. Or the condition or something.
The condition of something.
The matter in hand, or the issue, or the crux. Ah, I think. Oh, okay. Yeah, thank you. Oh, I see. Yeah. Yeah, foundation within a few lines.
Oui, je pense que ça soit vrai parce que là, c'est genre.
I would imagine, actually, he might be quite inspiring, actually. Because he had a reading the idea, how can you do, and what's our opinion?
Ouais, c'est vrai que ça dit clairement.
It's a very interesting question, yeah. Where's the alley gone? It's 2 o'clock. Which is the car? Suppose the chair, which is the man people coming here. Who's the chairperson? Huh? No? Sure, yes.
Oui, ça, oui, je veux des voitures. Tu vas voir deux pôles là, c'est deux ça va aller.
la machine avant la lettre.
Okay, I think we can start. Okay. So the first speaker, Alexandre, can continue is another one.
Thank you. So, some people made several remarks to me, which I would like to start with these remarks. So, first of all, I kind of diminished the contribution by Grothendieck to this field. It was him who noticed the first that the Galois group acts on pictures, and it was him who noticed that this action is faithful because of Galois theory. So it is an important contribution. The second thing is the answer to my question. So the correct number of maps with these characteristics, vertices, 6 edges, vertices of degrees 6, 3, 2, 1, and faces of the degrees 6, 3, 2, 1. The correct answer is 18. When I started to look at this example, I myself found 7 and even was able to convince myself that the answer is correct, that there are no more. But gradually we have found more and more of them. So here is one of the speakers obtained a remarkable result, 16, which is very close to the correct answer. Another remarkable result is 20. Why 20? If you enumerate the permutations, you get 20 triples of permutations, but 2 of them correspond to not connected maps. And in these 2 non-connected cases, one of the maps is on the torus, because the Euler characteristic remain the same, so you need 2 plus 0. Okay, the number of vertices, faces and edges is the same. And if you try to check your answer using the character table of symmetric group, you obtain 19 and a half. Why and a half? Because one of the maps, one of the non-connected maps, has a non-trivial automorphism, and the maps are counted not one by one, but every one of them is counted as 1 divided by the number of automorphisms. So you get 19 and a half as an upper bound. Just to add that among the 18 maps there are 8 with the cartographic group Mathieu M12, 6 with the cartographic group A12, alternating group, and 4 more with the imprimitive cartographic group, which means that the Belli functions can be decomposed in a composition of 2 functions, one of degree 4 and the other one of degree 3. Well, that's all concerning this example. And also, people remarked that I spoke at length about modular field, but I never gave a real definition. To me, this definition is too abstract, but nevertheless, sometimes in mathematics you must be abstract. So let gamma be the absolute Galois group or universal Galois group, that is the automorphism group of the field of algebraic numbers. And let D be a Dessin, a map. And let gamma D be a subgroup, the subgroup of gamma, which stabilizes the Dessin. So it contains all actions, all automorphisms, which preserve, which give the same picture. And then, so this action doesn't change the Dessin, and gamma acts on the cosets of this subgroup. This action changes the Dessins, but the orbits are finite, since in the same orbit you can only have the Dessins of the same set of degrees, of vertices, faces, and so on. Therefore, gamma D is a subgroup of finite index. And we take, as is usual in Galois theory, we take a subgroup H of gamma D, which is the maximal normal subgroup, not of gamma D, but of gamma. And this group preserves all the Dessins in the orbit and also has a finite index. And there is a main theorem of Galois theory that there is a bijection between subgroups of gamma closed in the Krull topology and the field extensions of Q. So if we pursue, if we go further in this way, we must explain what is Krull topology and many other things. And by the way, there is in the English version of my book, which is corrected in the Russian translation, there is a false statement at this point. It is stated that all subgroups of finite index are closed, but it is not correct. There are some very fancy examples constructed with ultrafilters, so it is too far away from pictures. Well, so subgroups of finite index correspond to finite, so closed subgroups of finite index correspond to finite extensions. Normal subgroups correspond to regular extensions, and K, let K be the finite regular extension of Q, which corresponds to the group H. And this field is the modular field of the Dessin. So, given this definition, I personally would be unable to work with it or to understand anything at all. I started to understand the definition when I computed an orbit about defined over a quadratic field, and I tried to simplify the field. And during a week I tried to simplify the field. It didn't work. I tried to replace square root of -14 by square root of -1, and then I understood finally that this field cannot be changed or cannot be chosen arbitrarily. It is some objective field. So, an additional remark: what I didn't prove either. The Galois group acts not directly on the pictures. It acts on Belly functions, and to the same picture we can attribute different Belly functions if we put the picture in different ways on the plane or on the Riemann surface. So a thing we must also prove is that if f1 and g1 be two Belly functions corresponding to a Dessin, and we act on these functions by Galois group and obtain f2 and g2, these f2 and g2 correspond also to the same Dessin d2. So the action is in fact not only on Belly functions but on Dessins. And the other remark is that the orbit is, if the orbit is of size n, then the index of gamma d is n, and therefore the modular field is a splitting field of a polynomial of degree n. Okay, so the abstract part is finished. I don't like it very much. My personal taste is rather like that. An example of what may happen, a Galois invariant of different nature with respect to those I showed before. So let us consider this particular orbit. So there are exactly three, not less, not more, black vertices, all of them of degree m. M is a parameter. The central vertex is of degree 5, and there are two faces of degree 1 and the outer face. Okay, the number of white vertices is okay, here is 5, so 3m minus 5 white vertices of degree 1. When m may even be equal to 2, then this map disappears, only this one remains. So it is unique and therefore defined over Q. For m bigger than 2, there are two pictures, and there are two possibilities. Just looking at the picture, it is impossible to guess which one holds. Two possibilities. Either two of them are defined over Q and form two separate orbits, or it is a quadratic orbit and then over a real quadratic field. Real because both maps are symmetric, are axially symmetric, mirror symmetric to themselves. Well, then we take a computation and we obtain that it is quadratic field, square root of delta, where delta is like that, function of m naturally. M is a parameter. But the question remains, can this delta be a square? If it is a square, then this quadratic orbit splits into two orbits over Q. Well, step by step. First of all, these two factors are coprime. Just a direct application of Euclid algorithm. Second, only this term can be divided by 3. 3m minus 2 cannot be divided by 3. Cannot be divisible by 3. Therefore, 3 times this factor and 3m minus 2 should both be squared separately. Then we write that this thing is a square, this thing is a square, and we remark that a square minus 2b square is equal to 1. And this is the most classical Pell equation whatsoever. But there is an additional condition, however, that a should be multiple of 3. It should be divisible by 3. So, in fact, the Pell's name was attributed to this equation by an error. The story began with Pythagoras, which proved that the equation a squared minus 2b squared equal to 0 doesn't have any integral solutions. So let us take the closest possible number, a squared minus 2b squared equal to 1, and it was already studied by Indian mathematicians starting from 7th century. Then by this team, Fermat, Euler, Lagrange, Abel, and so on, by Dirichlet. Well, what is known about this equation? There is the smallest solution, 3, 2. There are infinitely many solutions, and all of them are obtained by multiplying this initial solution by this matrix. Now, I would like to find the solutions where A is divisible by 3. So I reduce everything modulo 3. Here I obtain 0 and minus 1. It is more nice like that. A is equal to this matrix. A squared is equal to this matrix. So it only changes the sign of the initial solution. So every other solution, every solution with even index gives what I need. Therefore, all solutions, all cases, without any exception, all cases when this set, when this combinatorial orbit splits into two Galois orbits, are enumerated like that. We take the first solution and we multiply it by, not by the matrix A, but the matrix A squared, which is like that. Okay, and then M is defined as A squared plus 3 divided by 6, and these are the first numerical values. So the first case when the orbit splits into is when M is equal to 1634. And the growth exponent of the parameter M is, so every next solution is more than 1000 times greater than the previous one. Well, so this example is finished. Now I return to what I promised. Voilà. Brings curve. So I will construct very explicitly the algebraic curve of genus 4 and the Belli function of this surface, which gives as pre-image of the segment 01 the embedding of the graph of icosahedral into the this surface of genus 4. The significant part, more than half of the work, was done by Felix Klein in the 19th century. So I will construct the Belli function not for the map itself, but for its double. That is, I draw the map and its dual together. These parts, I draw them in blue, but in fact they are also black. So this is a black vertex and this is also a black vertex. I have shown one face of this map. Okay, so we have twice 12, so 24 black vertices, all of them of degree 5. Here there are other edges also like that and like that and so on. 30 white vertices which used to be of degree 2, now they became of degree 4. All the faces are now of degree 2 here. And there are, instead of 60, there are 120 edges. For this map I will construct Belli function. Okay, so who is Bring? Erland Bring was a history professor, an amateur mathematics. It was the period before Abel and Galois, so there still was a hope to solve an equation of 5th degree. And he invented a transformation which transforms a generic equation of degree 5 into such a form, only ax plus b here. So Felix Klein, in his book The Icosahedron and the Solution of Equations of the 5th degree, considered a curve, a projective curve in the space, in the projective space of dimension 4, which is defined by the following equations. So you see, if we take the roots of this equation, the first 3 elementary symmetric functions vanish. And therefore also the first 3 power symmetric functions vanish. So the sum is equal to 0, the sum of squares is equal to 0, the sum of cubes is equal to 0. a system of degree 6. And he called it the Brink's curve. There is an obvious automorphism group of this curve, S5, it permutes the coordinates. So the equation P of x equal to 0 usually have 5 roots, and there are 120 permutations of these roots, which give 120 different points, 120 points on our curve, which are usually different, but not always. So, I take the discriminant of our polynomial, here is the discriminant, and I affirm that the Belly function is like that. The first part of the discriminant is divided by this discriminant. Notice that f minus 1 is equal to, here the sign minus, okay, the second part divided by the same discriminant. Well,
So this is the Belly function for the curve, what you can find it.
yes,
Okay.
it is a Belly function defined on this curve, and whose inverse image of the segment 0, 1 gives not exactly the icosahedron, but the icosahedron together with the dual.
So this is inclined book.
Hmm?
You said this is inclined book. This is a function.
No, Klein, you used another covering. Find the covering of this curve over the sphere with 12 ramification points. These 12 ramification points are the vertices of the usual icosahedron. Okay? And every ramification has a type 2, 1. So one critical point of multiplicity 2 and one non-critical point. And this is the pre-image of the icosahedron according to this covering is our icosahedron of genus 4, in which all faces are triangulated. We put a vertex inside each face. And well, so note that A is a polynomial of degree 4 in our coordinates, and B is a polynomial of degree 5 in our projective coordinates. Okay? So, if we take roots of our Belly function, first of all, we may remark that all vertices are of degree 5. All roots are of multiplicity 5. Okay, so all the pre-images of 0 are of multiplicity 5, which is okay, they are black vertices. And if we add this equation of degree 4 to our system, we get 24 solutions, because the system, the initial system, was of degree 6. So it is okay with f equal to 0. From the point of view of polynomial, if a is equal to 0, we get the equation x5 plus b, and b may be chosen arbitrarily because we are in a projective situation. So we consider the equation like that. For example, there are 5 roots of unity which may be permuted in 120 ways, but some of these sequences are proportional. For example, this sequence of roots is proportional to this one, so they represent the same projective point. This is why we get, instead of 120 solutions, only 120 divided by 5. Now f minus 1. First of all, we remark that all pre-images of 1 are of multiplicity 4, which is okay because all our white vertices are of degree 4. And B is a polynomial of degree 5. If we add it to our system, we get 30 solutions. Everything is okay. So everything can be explained in terms of this equation, P equal to 0. So now B is equal to 0. And we should take A not equal to 0 arbitrarily. If we consider this equation, for example, one root is 0, the roots, the fourth roots of unity can be permuted, and they are proportional, and so on. The same discourse as before. Now, faces. Faces correspond to poles, and here is the denominator. We may recall that this denominator is was by construction the discriminant, and the discriminant is a square of something. Okay, so all poles are multiplicity 2, and this equation is of degree 10, and so we get 60 solutions, and so on. And okay, this can also be explained from the point of view of our polynomial of degree 5. We can, if discriminant is equal to 0, we can take an arbitrary pair of roots, equate them, and then the other roots can be permuted in 6 possible ways. Good. So this is a reminder. I showed you once that because of icosahedron having many automorphisms, its Bernoulli function can be decomposed in many different ways. So if we take, for example, the quotient by the rotation of order 3, we get this map, and then this one may be quotient by the rotation of degree 2, and so on. Here is, this is a function, this is a picture of degree 10. Here is the quotient by the rotation of degree, degree 5, and so on. So in the language of pictures, not in the language of functions itself, which should be computed themselves, but in the language of pictures, it is rather easy to construct all these decompositions. Now I will work with this particular one, just to understand what takes place. So we have, it seems that there is a little error here, but okay, it will be corrected later. So what can I do with these pictures? I applied last time when I constructed the embedding of the icosahedron into the surface of genus 4, I applied the transformation. I replaced the permutation sigma, which showed the rotation of edges around the black vertices, by sigma squared. I can make the same operation with all the maps of the previous chart, and I get something here of genus 2, and here of genus 1, and here of genus 0, and so on. So I'm sure that the Bernoulli function for the icosahedron can also be decomposed in many different ways according to this chart. So I will take this particular picture and look what takes place. Okay, so you see here was an extra vertex which should not be. there. Okay, so this picture is obtained, the first picture above is obtained from usual icosahedron. We take it by two opposite vertices, and these vertices remain intact, but the 5 edges attached to them become one edge. So the vertices become the ones of degree 1. Okay? There are 5 triangles which form one triangle. There are 10 triangles in between which form 2 triangles, and the same thing below. So finally we get 2 vertices of degree 1. Okay? And all the faces are triangles. You have triangle, 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 and the outer face is also triangle. Now I replace sigma with sigma square. You see here is 1, 2, 3, 4, 5, and here is 1, 3, 5, 2, 4. Okay? And what I get is the image, the quotient of the ring icosahedron by the rotation of order 5. Necessarily, because I apply the same transformation. And indeed, we see that there are still 2 vertices of degree 1, but faces became of degrees 5, 5, 1, 1. Maybe somebody remembers that when I spoke about this stellated figure, I mentioned that there are 2 faces which remain invariant under the rotation. These invariant faces became faces of degree 1. And the other ones just, the number is divided by 5. Well, so this is the image, the quotient of the Briggs icosahedron by the rotation of order 5. And maybe you recognize this figure. It is one of the example I considered yesterday. This one. Okay, all these maps have vertices of degrees 5, 5, 1, 1 and faces of degrees 5, 5, 1, 1. So this is the image of icosahedron. The other ones just came here by chance. So the idea is to cover these pictures in the following way. In the same way I did with the Briggs icosahedron, namely to consider coverings of degree 4, or of degree 5, with 4 ramification points. The vertices, both vertices of degree 1 and the centers of both faces of degree 1. Then the number of edges will be multiplied by 5. The 2 faces of degree 5 become 10 faces of degree 5. The 2 vertices of degree 5 become 10 vertices of degree 5. The vertices of degree 1 being ramification points also become vertices of degree 5. And the faces of degree 1 being ramification points also become faces of degree 5. So everything will become, all the vertices and all the faces will become those of degree 5. I can make this operation with all the 5 maps because their set of degrees is the same. So I need tuples of 4 permutations, each one of them just a cycle of length 5. 4 because there are 4 ramification points. It turns out that there are 60 tuples like that, and this already gives me 300 maps with all vertices and all faces of degree 5. And I know that among these 300 maps, one of them, namely one of the coverings of this figure, might bring the icosahedron. But which one? Okay, let's make a try. For this particular map, I find, first of all, its Belly function. Here it is. The black vertices of degree 1 are roots of this quadratic polynomial. The faces of degree 1 are roots of this quadratic polynomial. So let us try this ramification. This covering y to the degree 5 is equal to this fraction. It should give something with the same combinatorial characteristics. But is it? It is one of the possibilities among 60. Does it give the figure I would like to have? So the question is not easy to answer. The one thing is rather annoying but simple. How to see if two maps are isomorphic. Either maps are isomorphic or not. So what is the possibility? Of course not by hand, but I need some program which would verify the isomorphism. So it is theoretical. It is simple, but we need some help of computer. Okay, but this is not the most difficult part. The most difficult part is to find out what is the map itself. We have a completely explicit construction. All formulas are written, but what is the corresponding map? In the planar case, I just made a picture with the help of computer, and I saw the map in question. Here on the surface of genus 4, it is I don't know how to approach to this question. But there is a way around. So in genus 1, all algebraic curves are elliptic. In genus 2, all of them are hyperelliptic. Starting from the genus 3, the algebraic curves are subdivided into disjoint classes. The curves of canonical type and hyperelliptic. It turns out that our curve is hyperelliptic. There is a change of variables like that, and s is equal to y, which gives this equation for this curve. The other possible equation, another possible equation is like that, and it is hyperelliptic, while the Brinks curve is not hyperelliptic. It is a curve of a canonical type. Therefore, the maps cannot be isomorphic, and I learned that by this change of variables without even explicitly constructed one of the maps. One of them of the map, icosahedron. I know how to represent it. What is this map? I don't know. I didn't construct it in any explicit way, but I know that it is not isomorphic to the icosahedron. Okay, so this is the end of the story, and to finish, this is the marble floor of the St. Mark's Basilica in Venice. This mosaic is attributed to Paolo Uccello, and look at the year, it is 1430, so almost 200 years before Kepler. The construction of these figures is of this stellar polyhedra is attributed to Kepler. The publication of Kepler is 1619. This is 1430. Okay, and also I would like to propose to fill a bottle, not immediately but after the next talk, during the tea break. I looked for Chateau Petrus, but I didn't find but it is Bordeaux. Well, so there is nobody who gained, who get 18 pictures, including myself. I regret very much that I didn't take the list of the pictures with me, so I tried to draw them, I didn't arrive. So I deserve a little portion of it, but in the same way as the other. Okay, thank you.
Any questions? No, but I'm sure you have.
Yeah. No, this is beautiful. Yeah, beautiful, but I do not know if it's closer to botanics or to prime numbers. The pictures. In the long run, do you think there will be some rule?
Here is stellated, small stellated dodecahedron, which is
the theory of descent d'enfants is this surprise. So if you study all of them with 1,000 edges, you are not more competent for those with 1,001 edges, I think.
Well, when people discover some islands and see new animals on them, yes.
Okay, well, no question again, like I said.
If you have a descent could you have a way to detect its orbit and to have an idea about the Galois group?
To start with, I consider what we call combinatorial orbit. It is the set of Dessins with the same degrees of black, white, vertices and faces. But what happens inside the set needs, so there are a zoo of very different invariants, and sometimes we describe new ones we discover.
So your question is about the orbits under the dark. That's interesting. So not much you know about it. I see.
There are many examples which show that such invariant, such properties invariant, the other properties invariant. So we can detect from time to time. We can detect some interesting things.
I see.
So if you take the length of this combinatorial orbit,
yes,
divided by the length of the orbit, is it clear that this can go to infinity?
You mean are there Galois orbits of bigger and bigger size?
No? I mean that the difference. So if you have one point,
yes,
there's this combinatorial orbit.
Yes.
And then you take the real orbit, and you get it, or you get it somehow how far you're away from being the right
most often than not, all this set is one orbit. So usually we get a combinatorial orbit, and it is a Galois orbit. From time to time, we find something more.
But can you be extremely far away from things, or
yes, if you consider, for example, trees with 24 edges in So the average number of trees for a given set of degrees of vertices is more than million. So
The Galois orbits are much.
Huh?
The Galois orbits are much smaller. There could be several millions too.
It could be, so my belief is that most often than not it is just the whole set of several million elements, the Galois orbit.
Okay.
But to prove that, I should work with the systems of algebraic equations of degree more than million.
We don't think there's one extreme example where the combinatorial orbit is very large, like a few millions, but they all define over Q or something. All the Galois orbits are size 1 or something like something. You don't believe something like that?
No, I absolutely don't believe. I have an example when there are 3 maps and all of them defined over Q. But 3 is not
very large.
Yeah, not very large.
Okay, so let's speak again. So I guess in order to have a longer break later, we're going to start now.
Yeah.
No break. We're starting now. No break. Yeah, so this time schedule is a little bit now.